Okay, so go ahead and respond to the attendance poll if you have not done so already. There's one up there right now. Okay, and today we will take a look. We will continue our lectures on floating point numbers. And so on Wednesday we talked a little bit about the basics, and we said type double uses 64 bits to represent a number, okay? To represent a real number, but because we're using only a finite amount of information, this is equivalent to having only a set number of digits available on your calculator. And so because of that, we cannot represent all of the numbers on the number line. We can only represent 2 to the 64 different values. And we said the way the specification goes is it uses 52 bits for the mantissa, 11 bits for the exponent, because we're basically doing binary scientific notation, and we have 1 bit for the sign. And so here we said, well, let's try setting up kind of a miniature version of this, and we're just going to use 8 bits. We have 1 bit for the sign, 3 bits for the exponent, and 4 bits for the mantissa. And even though we have just a small version of this type double 64-bit thing, we can see a lot of kind of similarities, and also some of the unusual things that can result. Okay, and so we talked about the exponent and how it's biased. Okay, so what you see in this exponent, which is 101, which when we convert from binary to decimal, this will be equivalent to 5. We apply the bias of -3, and this will be equivalent to 2. So this will, we take the mantissa of 0111, and so this number in bits becomes 1.0111 times 2 to the 2, which turns into 5.75 in decimal, okay? And then we left off on Wednesday saying we have a few special values, okay? If the exponent becomes all ones and we have all zeros, then that's going to be infinity or negative infinity. And if it's all ones and something other than all zeros, then we get not a number, okay? All right, so today we will just continue talking, working through this mini float system, and we will just discuss some of the other things that we might encounter. Okay, so if we said 0, I'm going to just write my numbers like this: 0, 1, 1, 1, 0, 0, 0, 0. This is equal to positive infinity. Okay, so then we can ask, well, what is the largest value I can represent that is not infinity? Okay, so let's think about this. Okay, so if we're talking about our largest positive value, our sign bit will be 0. And so what's the largest exponent I can have that's not going to push me into infinity or NaN? 110, right? Okay, and then what will be the largest the largest mantissa that I can then have? All ones, right? So this is what we'll have. All right, so what does this become? All right, so if we look at this, the exponent will be 4 plus 2 plus 0. So that's an exponent of 6. We apply the bias, and so I have 3. So this represents, this thing becomes 1.1111 times 2 to the 3. Okay? And so we have a few ways we can do this. I can just kind of roll over the decimal 3 spots. And so this becomes 1, 1, 1, 1.1. And that is going to be 8 plus 4 plus 2 plus 1 plus 1/2. And we get 15.5. Okay? So the largest value my 8-bit floating point number thing can represent is 15.5. If it gets any bigger than this, it's going to say it's infinity. Okay? So this is the largest value I can have. It's 15.5. Anything bigger becomes, in its mind, infinity. All right. Now that seems silly because we're like 15.5. That's so small, especially compared to infinity. But our computer, which has 64 bits at its disposal, still has the exact same problem, okay? It reaches a big number, or what is considered to be big, where all these bits are filled out as ones, and it's, you know, the exponent's pretty much 1, 1, 1, 0, okay? It reaches that point, and it says, oh, it's bigger than this, now it's infinity, okay? This value, this is called the machine, in our case, double max, all right? Because it's type double, it's going to be machine double max. And so if I go to R, and I come along here, all right? And if I say dot machine double x max, this is the biggest number I can represent, 1.797. Let's see, let me make this a little bit bigger. Okay, this is pretty much the biggest number I can represent. Anything bigger than this is going to turn into infinity. Okay, so I think if I do 10 to the 23, I get something like this. Okay. And if I do 10 to the 2 times 10 to the 23 plus 2 times 10 to the 22, you know, I get something pretty close to this. So if I do like sum of 2 to the 1023 to okay, so here I get a number that's pretty much like our machine double x max. Okay, I get, technically I think I can go all the way down to 1. No, then it breaks down. Okay, but basically, if I take this number and I try to add something else. Okay, so if I take if I say this is going to be the value a, and I say a plus 2 times 10 to the 22. Okay, because it can tell me what 2 times 10 to the 22 is, and it can tell me what a is. But if I say, what is a plus 2 times 2 raised to the 10 to the 22, it tells me it's infinity. Okay, because I've hit the maximum value I can represent. If I try to do 2 to the 1024, it blows up and it says that's infinity. Okay, we are no longer able to represent values bigger than basically this number, okay? So 2 to the 1023 plus 2 to the 1022 plus all the way probably around to 2 to the 1000-ish, something around there. That's about what our machine double max is. And anything bigger than this, it's going to say it's infinity. Now this is on the order of 10 to the 300 power, 10 to the 308 power. So probably for most of our jobs, this is big enough, right? This is more than the number of atoms in the known universe and things like that. But it's also very short from infinity, right? It's nowhere near infinity. And so, you know, when we only have 8 bits, the largest number we can represent is 15.5, and if we were to try to represent anything bigger than that, it turns into infinity, okay? So this is, I guess, dot machine, $, double max. So for 64 bits, it's approximately, what is it? 1.797 times 10 to the 308, okay? It's approximately, you know, a little smaller than 2 to the 1024, okay? 2 to the 1024 will be infinity, because with 11 bits for the exponent, you know, and the bias and whatever, the biggest exponent we can represent is 1023. So anyway, that's this is what we have. The largest value I can represent that is not infinity is going to be 15.5. Okay, what's the next smallest value? The next largest? The next largest would be 0, 1, 1, 0, 1, 1, 1, 0, right? So this part is still 2 to the 3. The exponent still is 3 after bias. And so this becomes 1 point, and we just copy the mantissa over after the binary point times 2 to the 3, and this becomes, so if I roll the point over 3 spots, 1, 1, 1, 1.0, 8 plus 4 plus 2 plus 1 plus 0 halves, and this gives me 15, okay? So the largest value I can represent is 15.5. The next largest would be 15, so on and so forth, okay? So, so that's what we have on the large side, okay? On the small side, we run into a problem, okay? And that is when we, one of the things we specified is that this mantissa part, we're always going to assume the mantissa has a leading 1, okay? And if we always assume that the mantissa has a leading 1, then we have no way to represent 0, okay? So, you know, if we always assume mantissa has a leading 1, we cannot represent 0, okay? Because if I tried to do 0, 0, 0, 0, 0, 0, 0, 0, okay, under the current rules, what happens is my exponent is equal to 0 minus 3. I get an exponent of negative 3, and the mantissa is 1.0000 times 2 to the negative 3, and this becomes 1/8, okay? And I am not able to represent 0. So what I need is we bring in an exception, and we say if the exponent is all zeros, we are going to enter what's known as denormalized or subnormalized mode, okay? So we have an exception to the mantissa always has 1 rule, okay? If the exponent bits are 0, 0, 0, or are all zeros, we are in denormalized or subnormalized mode, okay? And what this means is the leading digit in the mantissa will be 0, okay? But to avoid some other issues, we have to modify our bias, okay? Okay, so in denormalized mode, mantissa will have a leading digit 0. Okay. And we modify our bias to be 1 less than usual. Okay, so normally we apply a bias of 3. Now we apply a bias of 2. Okay. Is usually -3. Okay. Now our bias, or I don't know. Our bias is usually, I'm going to just say our bias is usually 3. Now our bias is 2. Okay, and this kind of helps smooth out, you know, the number line. Okay, and the reason why is because if we think about what our smallest normalized value, so if we have this, our smallest normalized value will be 0, 0, 0, 1, 0, 0, 0, 0, okay? And so here our exponent is equal to 1 minus 3 equal to -2. And this is 1.0000 times 2 to the -2, and I have 1/4, okay? And what we're going to do is when we switch to denormalized mode, so let's just think, you know, what's the what's the largest value that I can represent that's smaller than this value, okay? Okay, so what's the next biggest number I can represent? We will have to enter into denormalized mode, right? Because this is the smallest value I can represent where the exponents are not all 0. And if I go into exponents are all 0, we're going to enter denormalized mode, okay? So when we make the exponent bits all 0, we are denormalized. Okay, and this is going to become 0, 0, 0, 0, and then over here, maybe I'll want to put all 1s. This will be the largest denormalized value. Okay, and so this will become, our leading bit becomes 0. Our leading digit becomes 0, but now we have all 1s here. Okay, and so to kind of keep this on the same scale as this, we're going to keep this to be 2 to the -2. Okay, so just to kind of keep our step size consistent, we move this up to, we change this to be 2 to the -2. So our exponent is going to be 0 minus 2 equals -2, okay? So the bias is 1 less than normal. Is that okay? Yeah.
Also one less than normal for 64-bit.
Same thing. Yeah. So in a 64-bit floating point, we have 11 bits for the exponent. Our bias is normally 1023. When we enter denormalized mode, our bias is 1022. Okay. Yeah. So it's the same rule set. We just have more bits to play with. Okay. All right. So this becomes denormalized mode. All right. And so so what does this become? All right. So this is if we look at this in denormalized, this is 0 plus 1/2 plus 1/4 plus 1/8 plus 1/16. Okay. Times 2 to the negative 2, so 1 over 4. And this becomes so here I have 15 sixteenths times 1/4, and so we get 15 64ths, okay? Which is very close to 1/4, but just a tiny bit smaller, okay? So the smallest normalized value I have is 1/4, and then the largest denormalized value I have is 15 64ths. Is that okay? Okay. So let's talk about what is the smallest possible, what's the smallest positive value I can represent that's denormalized, right? Smallest positive denormalized value. It's going to be 0. What will my exponent be? 0, 0, 0. And what will my mantissa bits be? 0, 0, 0, 1. Okay. So here my exponent will be 0 minus 2. Okay. So I have an exponent of negative 2. My mantissa becomes 0.0001 times 2 to the negative 2. So this becomes 1/16 times 1/4, and I get 1/64. This is the smallest positive denormalized value. Okay, and this will be your dot machine Xmin. So this is the smallest possible value I can represent on the computer. So for double Xmin, okay, it's on the order of 10 to the negative 308. Okay, I think it's equivalent to 2 to the negative 1020. Yeah, 2 to the negative 1022. Sorry, 2 to the negative 1022. I think, what happens if I do? All right. All right. Well, anyway, okay. Dot machine $xmin. So on PC, or basically on Intel chips or all computers, this is for 64 bits. It's about 2 to the negative 10. I'm sorry. It's actually less than that. Well, all right. I'm not sure. Okay. So anyway, smallest possible denormalized value we have is 1/64. Okay, and then again, then 0, 0, 0, 0, 0, 0, 0, 0 just becomes 0. Okay, let me pull up a piece, a little, I don't know, worksheet that I started making. And so I'm going to just talk as far as mini floats go. Let me blow this up here. How do I zoom in here? Okay, so this is our mini float with 8 bits, okay? So this will be in decimal. Okay, so we'll have 0, or maybe not decimal. All right, I'll just say. All right, over here I have 0.0001 times 2 to the negative 2. So this becomes basically what's wrong with this? 1/16 times 1/4, and we get 1/64. Okay, and over here I have 1/8 times 1/4, and I get 2/64 or 1/32. Okay, and then over here I have 1/8 plus 1/16 quantity times 1/4. That's not what I wanted. That's smaller. Okay. So here I got 1/8 and 1/16 times 1/4, and so that will give me basically 3/64. Okay. So on and so forth until I get to the. So these are all denormalized, right? And so the largest denormalized, then this becomes 15/16 times 1/4. So we've already seen all of this. And we get 15/64 right here. Okay, so 0, 0, 0, 1, 1, 1 becomes 15/64. Okay, and now this is the smallest normalized value. And this is 1 times 1/4. And so here we get 1/4, okay? So all of these, our step size is 1/64, right? We're incrementing by 64ths. I start off with 1/64, 2/64, 3/64, all the way up to 15/64, and now I'm at 16/64, okay? So my step size is 1/64, okay? When I go up to here, I have 1 plus 1/16 times 1/4. Okay. I'm going to just do times 1/4. Okay. So 1 plus 1/16 times 1/4, and so what will that give me? (17/64), right? So our step size is still 1/64, okay? Step size is still 1/64. Why is my step size still 1/64? The reason is because with 4 bits behind the mantissa, I can represent values as small as 1/16, and with my exponent being 2 to the negative 2, 1/4, I can, every time I change that last bit, I'm changing it by 1/64, okay? So smallest bit is 1/16, exponent is 1/4, so step size is 1/64. Okay, now I come to here and I have 1, 1, 1, 1, so this is going to be 1 and 15/16. times 1/4. And what does this become? 31/64. Okay, so we're just shy of a half. All right, and so when I get to here, what do I have? I have 1.0000, okay? So I have 1 times 1/2, and I get 1/2. And this next part, this is the beauty of floating point arithmetic. It's hard to see it, okay? All right, but the next largest, the next value I can represent in floating point will be, the exponent is 0, 1, 0, and then I have 0, 0, 0, 1. Okay, so I have 1.0001 times 2 to the negative 1. So this is 1 and 1/16 times 1/2. Okay, and what is that? (1730 seconds). 1730 seconds. Okay, and what is the next thing I'm going to have? 1 plus 1/8 times 1/2, and we're at 1830 seconds. Okay, so our step size here is 1/32. Okay, so while I was when I started at 0 and going all the way up to 1/2, my increment was 1/64. Okay, but now that I'm dealing with numbers bigger than a half, okay, I can't keep track of these 64ths anymore. I can only track of up to 30 seconds. Okay, and so I get up to here, and this is 1 and 15/16 times 1/2, and what is this? This is 31/32. Okay, 31, I think. 16, 30, 31, 16th, yeah, 30, yeah. Okay, so we get up to there, and then and so now I have 1.0000 times 2 to the 0. Wait, did I do this wrong? Oh, maybe this is this 1 and 30 seconds? I'm trying to, hold on. It's not. Oh, I wrote this wrong. Okay, so I meant to write the largest here. So 1 and 15/16. Why am I having trouble here? 16 plus 15, so I have, this is correct, right? Okay, and then so now, oh, duh, okay, this is just 1, okay, I was having trouble, so this is 1 times 2 to the 0, which is 1, and is 1, I was like, why am my brain just stopped working for a second. Okay, so we're at 31/30 seconds, and now we're at 1. Okay, and so when this is my exponent is 0, 1, 1. Okay, the next size thing is going to be basically 1 and 1/16 times 1. Which gives me 1 and 1/16, okay? Yeah, I guess 17/16, we can write that, okay? And so now my step size is 1/16, okay? So as we've moved up, our step size increases, and so on and so forth until, how do I insert a row in my table here? No. Okay, so I'm going to write step size is 1/16, And basically, this kind of pattern keeps going until until we get to the max, where the largest value we can have is 1, 1, 1, 1, 1, 1. Here, I'll do the one right before it, and the one right below. And I think we established this already. So this is, I'm sorry. There we go. Okay. So here I have 1.11110 times 2 to the, what is this, 2 to the 3? Okay, and this turns out to be 15. And then I have 1.1111 times 2 to the 3, and this becomes 15.5. Okay. And so our step size is 1/2. Okay, and now we run into getting into infinity here. But basically, as when your values are small, the number line. So this is the floating point number line. Okay, and we'll just look at the positive half, or non-zero side, okay, or non-negative side. It looks like this. So in the beginning, things are spaced out really small, okay? So here's 0, and up until we get to, what did I say, 1/4, oh no, up until we get to 1/2, our step size is 1/64. Okay, so I'll say, so this is 1/4, this is kind of the denorm zone, until we get to 1/2, our steps here (1/64), okay? And then once we get to 1/2, our step sizes are a little bit bigger until we get to around 1. Okay? Okay, and if we continue that all the way up until and after 1 until we get to 2, our step size is only 1/16, so on and so forth until and then the step size is 1/4 until we get to basically 1/8, sorry, I can't do math today. And the step sizes keep increasing until we get to some point where it reaches infinity, right? Okay, and so there are, so as the values increase, the spacing gets wider, okay? As values get larger, spacing gets larger. And there's, so there are some weird consequences, okay? Okay, so here's a question. All right, so dot machine max, or double max, whatever it is, okay, is on the order of 1.797 times 10 to the 308 or something like that, okay? What if I just ran a loop, okay? And I just wrote while true. Okay, we're gonna just start off with x equal to 1. And I did this. Okay, and I just let this run for hours, maybe days. Okay, so it's just counting by 1. It keeps counting. All right. If I let it run for a long time, and I come back a year later and I say, all right, computer, what is x? What will x be? It will not be infinity. Okay. Huh? It won't even be double max. It won't be 0. We'll have gotten past it, you know. Huh? It won't be 1. No, I mean, here. I mean, we can just start off, right? Okay.
You never update the x in the environment.
No. That's not. It's not one of those type of trick questions here. Okay. All right. So I'll just show you. So here, x is 1. Okay. And I'll just do this. While true. Okay. X becomes x plus 1. All right. And we'll just run this. Okay. And then so, if I let this run, like, we can just count for like 1, 1,000, 2, 1,000, 3, 1,000, 4, 1,000, 5, 1,000. Okay, and then I'm just going to stop it, interrupt it. X got pretty, it counted up to 260 million up to this time, okay? All right, and we don't have time to get all the way to the end, but I'll show you where we start to get close. What is, I don't know. 10 to the 1020, no, hold on. Why am I having, oh man. Oh, I forgot the number. It was a big number, but it gets stuck. Okay, hang on. Let me look this up. Double precision. Oh, that's right. 2 to the 52. I think, or 2 to the 53. Yes, that's the one. Okay, so I'm going to go ahead and do digits or option. Digits equals, I think, 16, 17. I don't know what I think we can go. Could not find option. Oh, options. Digits equals 15. Okay. So let me do 2 to the 53. Okay. So when I get 2 to the 53, I'm going to just store this as D. Okay. If I do D minus, we're going to just, we'll backtrack 10 points, okay? So D minus 10, okay? So I have D. D looks like this, okay? And I'm going to do, we're just going to repeat D equals D plus 1, all right? I'm going to just run this a few times, okay? So I run this. Okay, it's counting up 84, 85, 86, 87, 88, 89, 90. Okay, so far so good. 91, 92. Uh-oh. What has happened? It got stuck, okay? It got to a point where the increment on the number line is no longer 1, but it's 2. Okay, so remember we're able to go from whatever 1/32 to 2/30, whatever it was. Okay, we're able to go, but we got to a point on the double precision number line where our increment is bigger than 1, and so when we add 1, it's stuck. It doesn't know. It can't differentiate between this number and one bigger than that. But I can add 2 now, okay? Because we're talking bits and we're talking powers of 2, so I can add 2. I can add 2, but if I try to add 1, it can't differentiate, okay? Yes?
If you add 3, will it only add 2?
I think it'll, let's see. So we're at, so right now, D is this. If I add 3, it adds 4 to it, okay? But if I try to add 1, it can't do it, but I can add 2, okay? So there are things that we have to be aware of when we are dealing with double precision floating point, okay? This is, I don't think you guys would have expected this to have happened, but if we think about it, okay, because we're using just a finite number of bits to represent values, we can't represent all the numbers on the number line. And we're in a range where our numbers are so big that the spacing is larger than an integer, okay? And so adding 1 and things like that. And so, so we run into issues, and so this is just something we have to be aware of. When we do our sorts of computations, you know, we talked about, okay, we saw, you know, 0.1 plus 0.2 doesn't equal 0.3 because we have binary approximations, okay? And we also run into places where stuff like this happens, okay? All right, we'll end here. Have a great weekend, and we'll see you guys on Monday. Or is there a holiday on Monday? I don't know.
Yeah, holiday.
There's a holiday on Monday. Okay, all right. Well, we'll see you guys next time.
Yeah, I enrolled in the next lecture.